This is problem 4-27M. It's on page 233. Compute the angle of twist of the free end relative to the fixed end of the steel bar shown essentially in the figure below. Okay, so we have a bar that has a varying size. So it's got a larger size on one end and a smaller size coming out continuing. So my drawing's not good. You can see it there in your book. Basically, there's a torque on the end. I'm not going to draw the disc on the end. In fact, I'm going to use a different terminology so you guys get used to it. So there's the torque. And have I drawn that torque in the right direction? Is it correct according to what the book has? No, because the torque in the book is this way. So I need to reverse my arrow. Doesn't really matter as far as the stress is concerned. No, but for consistency, I'll draw it the right way. Okay? So this torque is a 200 Newton meter torque. And by the way, for the sake of the video, this is 4-27. So the back end of this is fixed. I won't draw the wall. I'll just put some crosshatch there to indicate that it's fixed. You got the dimensions there. Now let's think intuitively about what's going to happen here. Forget this small section for just a minute. Well, actually, let's consider the whole thing. If you were to cut the beam or the shaft here, how much torque does this section have to apply to this section to keep it from rotating? 200 Newton meters. It's just an equilibrium. So basically, this section of the shaft has to, let's see, this, we're applying a twist this way. It's got to twist this way with 200 Newton meters to keep the thing from rotating, right? So if we were to cut it, we'd expect to find 200 Newton meters. In fact, notice it really wouldn't matter where you cut the shaft, you'd find a torque of 200 Newton meters. Does that make sense? So the point here is that if we were to make a torque diagram in Newton meters along the entire length of the shaft, you'd find the same level of torque until it drops off at the end. We're going to start making diagrams like this where we look at loads over the length of the beam or the shaft or whatever it happens to be. Does that make sense? Okay, so the torque is constant throughout. Does it matter that the section that's resisting that torque changes in size? No. Would you expect intuitively for the stress to be higher in this section or this section? What do you think? Small section, right? There's less material there. It's not out as far, right? So the stress is going to have to be higher to supply the same level of torque. So we expect, if we were to make a shear stress diagram versus length, you would expect to see a step in it here, right? Now, let's go back and see what they asked us to do. Compute the angle of twist of the free end relative to the fixed end. So we don't have to look at this from the very beginning, right? We can ignore all of this and just answer the question, what's the angle of twist out to this section? Let me call that section 1. So that's somewhere along the length, okay? So the torque is still the same. It's still 200 Newton meters. But how do we calculate the angle of twist? Well, it turns out, I should have moved forward in the slide before I said this, before I started this discussion, but basically the angle of twist is just given by this equation, because remember before I said that the torsional stress is just proportional to the strain, and the strain could be measured in radians. But if the torsional stress is Tc over J, then you can solve for theta, the strain, as Tc over Jg, right? Actually, I didn't do the same thing, did I? Well, what's different? Well, what's different is that in this equation, the longer the rod, the more the angle is going to change. Does that make sense? So I'm missing a step in here somewhere. I should have thought about that before I wrote it. But you can see how that would work, right? The higher the torque, the more the rod should bend, right? The longer the length, the farther it's going to turn. Okay, the stiffer it is, the less it's going to turn. That's based on geometry. And the stiffer it is from the material, the less it's going to turn. So that's where that comes from. So basically what we need to do is use the equation that they've got there. Theta is TL over JG to solve our problem. I'm missing something. I think I'm missing something in this equation. I'll have to think about it, but I'll get back with you next time. There's something else in here that I'm missing, but I can't think of what that is right now. We'll get to that later. Okay? So if we want the angle, if we want to know how far this is rotated, let's see, I guess it would rotate the other way, right? So if we want to know that angle, theta 1, then we can calculate it. Now what length would we plug in? Well, just this length, right? So let's see if we can calculate theta 1. It should be pretty easy. It would just be the torque, 200 Newton meters, okay, multiplied by the length. Well, what is the length from there to there? Was it 1.2 meters? Is that what they said? 1,200 millimeters? It's 1.2 meters divided by J. Well, we need the polar moment of inertia for a circular section. Do you guys remember the equation for that? It's pi d cubed. No, that was the other one, right?
Pi d to the fourth over 32.
32, there we go. Good. And then we need G, so we need to know what material is it made out of. Now, I'm plugging in numbers, so let me go ahead. What was the diameter of this section, the larger diameter?
40 millimeters.
Okay, so 0.04 meters to the fourth power. Right? Okay, so I'm missing something. I'm missing G. Well, what is this made out of? Well, let's see.
Steel.
It's a steel bar. Notice they didn't give us the alloy. Why didn't they give us the alloy? It doesn't matter. It's about the same no matter what alloy you've got. Now, I should have looked this up too before I started this problem. Hey, I got lucky. Here it is, page 218. Here's a page you will probably want to mark because there are several different shear moduli here for different materials. The one we need is for plain carbon and alloy steels, and we're in metric units, so it's 80 gigapascals. Okay. You guys see it on table 4-3? So this should give us the deflection. Now, this is an angular measurement. What units will it have? Let's find out. We've got gigapascals here, but gigapascals are, I guess the easiest way to do it is to say that it's giga newtons per meter squared, because a newton per meter squared is a pascal, right, force per area. So it's just 10 to the 9th of those. So times 10 to the 9th newtons per meter squared. Well, now the newtons can go away. And let's see, this is meters to the 4th divided by meters squared. I've got a problem somewhere because it should come out dimensionless. Oh, no, here it is. Meter here.
So they'll cancel.
Okay, yeah, so all those cancel. Good. Let's say I did something wrong. You should always use units because I've caught myself making mistakes before by using units. But they do cancel, so I'm pretty sure this is correct. So plug it into your calculator, please. 200 times 1.2 over pi over 0.04 to the 4th power over 80 E9. You can multiply the whole thing by 32. Basically, you can take this 32 and move it up here, and you got the same thing. It's just inverting and multiplying. So this is going to be a really small number times a really big number. So anyone have an idea? What do you have? An answer? What do you have?
0.0119.
Second. 0.0119, thank you. Thank you for the second. This is non-dimensional, isn't it? Well, what kind of an angle is non-dimensional? Radians, exactly. These are not degrees, these are radians. Okay? So we can simply say these are radians. Make sure I don't go off the video, so I'll just erase it. Now, how do you go from radians to degrees? Because I don't know about you, but I don't have a good feel for radians. So what do you do?
Pi over 180.
Pi over 180. Well, actually, how about 180 over pi?
Oh, yeah, sorry.
That's all right. Degrees per radian. 180 degrees per pi radians. Well, you know the radians are gone. So what do we get when we do that? How much?
0.68.
So that's how far it rotates, less than a degree, a little over half a degree. That's how far what rotates, just this section. Well, do you understand that the small section will rotate by that amount plus some because of what happens inside of that shaft? Okay, well, let's figure out how far the second section would rotate. Well, it would be another angle like this, right? It'd be essentially the same thing. It would be 200 Newton meters, because it's the same torque in that section, multiplied by the length. The length of that section was, 400 millimeters? So 0.4 meters divided by, same thing, pi d in this section is 20 millimeters. So 0.02 meters to the fourth. Let's go ahead and put the 32 at the top, so we don't have to mess with that part. Okay, and then same 89 pascals. Units should go away again, just like they did before. So give me an answer if you would, please. This again will be in radians. .064? Well, now, does that make sense? Well, it's really hard to say, right? Because we know that the smaller section has a smaller diameter, and so its polar moment of inertia, J, will be different, but also it has a shorter length. But what we found here is that it twists more than the bigger section did, even though the bigger section is longer. Okay? So let's go ahead, since this is radians, and multiply it by 180 over pi, and see how many degrees this is.
3.6.
3.6? 3.6 what? 3, thank you. So 3.63 degrees. So basically the first section rotates by 0.68 degrees, the second section rotates by 3.63 degrees. How much does the whole thing rotate? The sum of the two, right? You have to add the two together, because you can think about it, if the first one twists by 0.68 degrees, all of the second one twists by that amount, plus it itself deforms, right? So this is just the extra deformation of the little section, that's all it is. Okay, so you have to add the two together to get the total. And someone already told me the number, but I didn't remember.
4.3 degrees.
4.3 degrees, thank you. So there's the answer they were looking for, was 4.3 degrees. Okay. Questions? Let me tell you the important parts of this chapter, okay? There's two equations from this chapter that are absolutely critical. This is one of them. The other one is this one. The stress is TR over J. Those are the main point. You ever watch a murder mystery? Okay? You know what happens in the mystery, the way the writers write it? At first everyone looks innocent, then all of a sudden everybody looks guilty, right? But most of them are red herrings. They're things that detract from the main person, right? The main person that did it. Well, these are the people that did it. These are the important things. Everything else in the chapter is sort of a red herring. Does that make sense? This is what you should focus on. Okay? Any questions? Comments? All right.